Now we are going to analyze this rational function using its asymptotes, the information we get from the first derivative, as a help to graph the function. So first of all, let's determine what the asymptotes of the graph are. First of all, as a shortcut for finding the horizontal asymptotes, we look at the degree of the top and the degree at the bottom, and notice that it's x squared over x squared. When the degrees are the same, the horizontal asymptote is going to be y equal to the ratio of the lead coefficients, which is 1 divided by 1. So it does have a horizontal asymptote of y equal to 1. In terms of its vertical asymptotes, we can tell at a glance what those are by any value of x that causes us to divide by 0, but the numerator is non-zero, and that occurs at 3 and negative 3. So we have two vertical asymptotes, x equals 3, x equals negative 3. And again, make sure that you list those asymptotes as y equal to 1, not just 1, and x equals negative 3, and x equals positive 3. Include the x's because you're giving the equation of a line, not just simply values of x. And then in terms of what the first derivative can tell us, the first derivative is, by quotient rule, the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. All right, what happens here is if we were to multiply this out, we have 2x to the third minus 2x to the third. That's going to be equal to 0, and all we're left with is, on the top, a negative 18x over x squared minus 9 squared. So to do a first derivative analysis of this function, we have critical values, which are values which cause the derivative to be equal to 0. That occurs at x equal to 0. And also where the first derivative is undefined. And that occurs at negative 3 and positive 3. So we have these three critical values, negative 3, 0, and 3. And in terms of our sign analysis of the function, first of all, we notice that the bottom is always going to be positive wherever the function is defined. So it really only depends on the numerator, the top of this derivative. And so negative 18x means that where it's defined, the function is going to be, the derivative is going to be negative whenever x is positive, and positive whenever x is negative. And again, wherever the function is defined and the derivative is equal to 0 at 0. So first of all, at negative 3 and 3, if you look at the original function, the function is not even defined there. So we can indicate that at negative 3 and at 3, the function itself is undefined. However, wherever the derivative is positive, the function is going to be increasing. So that occurs in the interval from negative infinity to negative 3, and then from negative 3 to 0. I'll emphasize that it's not increasing on negative infinity to 0 because it's undefined at negative 3. These are two separate intervals where the function is increasing. And then where the function is decreasing is where the first derivative was negative, decreasing and decreasing. And again, on the interval from 0 to 3 and from 3 to positive infinity. One other detail to point out, at negative 3 and 3, the function is undefined, and in fact we have vertical asymptotes at those 2 points. But at 0, we have the function increasing followed by decreasing, which would indicate that at 0, we do have a local maximum. So to summarize what the first derivative told us about the function is that the function is increasing on the intervals from negative infinity to negative 3 and negative 3 to 0, decreasing on the interval 0 to 3 and 3 to positive infinity, has a local maximum at x equal to 0, local minimum, well, it doesn't have any. And then it has horizontal asymptotes, and again, remember, write y equal to 1, not just 1. And then for the vertical asymptotes, x equals negative 3, x equals 3, and list those separately, because writing down simply plus or minus is not actually a number. So this actually produces what our graph would look like. Notice the horizontal asymptote, y equal to 1, the vertical asymptotes at x equals negative 3, x equals 3, and note where the function is increasing, decreasing, and it has a local maximum at x equal to 0.